Alright guys, we're going to be solving another question from the third chapter of the Meriam textbook, Engineering Mechanics, and in this one we need to determine the cylinder mass M1 required to cause loss of contact at point A. So we're going to start with the free body diagram. As always, we're going to have the free body diagram of the L-shaped beam. So we're going to have a tension in this cable, we can call it T. So we have a pin at point O. So we consider two forces, OX and OY, and call our X and Y in this direction. And we're going to have a normal force at point A. Can show it with A, which is supposed to be 0 because this question is asking us to have 0 contact force at point A. And we're going to have the center of mass in each part of this beam. We know that the AO part is 2/3 of the L, the whole length. And since we have a homogeneous rod, that means that the 2/3 of the weight would be in here. So mass times acceleration of gravity would be in there, and 1/3 in here. And if we just want to find the force D, we're gonna draw the free body diagram for the pulley. So we're gonna have two tension T in here, and the weight that is attached to that, or mg, and actually the mass is m1g. And from the question we know that the mass of the L-shaped beam is m, so this one would be actually m1. So if we just do sum of all forces in y for the pulley, we can conclude that our T would be 1/2 of the m1g. So now we know that our T is actually 1/2 of m1g. So we are in equilibrium. We're going to use our equilibrium equations. And if we just do sum of all moments about point O counterclockwise positive as always, we're going to get rid of all the unknowns at point O, and we're going to find the cylinder mass M1 with respect to the mass of the beam, which is M. And let's see what we have for that one. We're going to have the moment of the 2/3 part of the beam, and we can see the moment would be in this direction. So we're going to have a counterclockwise moment. So the force is 2/3 of mg. And since the moment is counterclockwise, we're going to put a positive sign in here times the distance of the beam. We know this angle is 30 degrees. And this side would be 2/3 of L times sine of 30. And because we know that the center of beam AO would be exactly at the center, so we're gonna have half of that distance. So 2/3 of L sine of 30 degrees, and we're gonna divide it by 2 since we need the little distance in here. So half of that, we're gonna have the moment of the 1/3 part, which is going to be clockwise, so negative 1/3 of mg. And the distance, this angle also is 30 degrees because we know this angle was 30 degrees. So since this angle was 30 degrees, we have a right triangle, which means this angle would be 60. So we have a right angle in here. And if you look at this green right triangle, this angle would be also 30 degrees because this would be 180, 60 plus 90. It's going to give this 130. So we're going to have L third cosine of 30 degrees divided by 2, since the center of gravity would be at the center of that. And we'll also have the moment of the T, which we found is 1/2 of m1g. And the distance this time is L third of cosine of 30 now divided by 2, and this will be equal to 0. So we can simplify this. We're just going to divide everything by g, so we get rid of g, can get rid of all the L13 here, 1/2 the same. So what we're going to end up from the first one would be the 2 will be canceled out with the sine of 32, so 2/3 of m minus 1/3 of m cosine of 30 is equal to m1 cosine of 30 degrees. So m1 in here would be, so this is going to give us 436 m, and that's going to be our m1, or the mass of the cylinder. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next one.